Okay, I think this is the last time, the last discussions. So I'm giving you two functions at the end. So probably I will start from the right one. Okay, let me just rewrite the functions. Okay, the functions is x with 2/3 and 6 minus x 1/3. Okay, the giveaway for, or the takeaway for these functions, if you look on this x with power of 2/3, this is rather we say a function that has some unique property. Okay? We will see later on. Okay. So if we try to derive, okay, and you can try do it by yourself. Try doing the product rule, FG, doing product rule. I will just write the results, okay, and write the conclusions for you. The first derivative, this will be simplified as 4 minus x over x with power of 1/3 and 6 minus x with power of 2/3. If you derive one more time, which means you are going to have the quotient rule. This will gives you this results. Okay. Now from these two equations, we can check whether the critical point or whether the maximum or minimum exists or not. But let's say we have the critical point when the first derivative is equal 0, which means that x is equal 4 from the first left equations, right? And we know from the denominator that the first derivative doesn't exist, or let me write the d and e, when x is 0 or x is 6, right? Because it makes the whole thing on the bottom part will be 0, right? So critical numbers, we can write that x will be 0, 4, and 6. So we may check the interval. Okay, we may check the interval. Check the interval. We can check 0, 4, and 6. I think when it's less than 0, which means it's negative, if we put negative inside this the first derivative, we will get by the top one is positive, the bottom one will be negative. So it will be negative for the left part. Let me take, maybe making this a little bit higher here. Okay. So this will be negative. Okay. And between 0 and 4, when you put any number between those two numbers, will be always positive, right? And then between 4 and 6, if you see 5, it's give away negative, right? It's giving the negative signs. And also if you increase the numbers, will be also giving negative. Okay. So it's decreasing, increasing, and decreasing. Okay. And if we try to look on the second derivative, we can check also whether the second derivative is positive or negative. Positive means it's concave upwards. The negative means concave downwards, which means we will have the minimum and maximum point. And eventually, when we try to draw, we expected at this x equals 0 supposed to be having a minimum. But when you try to maybe check with the computer or maybe using some graphic calculators, you will see that it's actually not this. Let me check. Not this. Over here. It's true that it's minimum, but it's actually will be having a sharp point like this. And also another thing that really based on our confirmations that this part, when x equals 6, remember that the denominator will be 0, which means that the tangent will be vertical because it's getting an infinite, right? So it's a vertical tangent, and this is a sharp point. So how do we get idea on sharp point? Okay, based on what we have found here, we know that we have found that probably in this x equals 0, it's going to be minimum. But we know that this doesn't exist. This is the giveaway. When x equals 0, it doesn't exist. So probably it's going to be a sharp point, or it will be like this 6. It will be a vertical tangent. And you need to check also the second derivative, how it looks like, the concavity. Okay. Later on I will construct a more precise procedure from the very beginning and then confirming the sketch at the end. Okay.
Let's say we have a sharp point down, like let's say the graph is like sharp point down like this, right? Can we say that that sharp point is the absolute minimum point or absolute maximum point? If let's say
yes, we can also say that. We can also say absolute or local. It depends on when you check the value. When you check the value, whether it's going to be really the lowest one on the interval or not.
The sharp point we can say.
Yes, we can make it as a minimum or maximum.
That means at that point the curve is not continuous, right?
Yes, it's continuous. But it doesn't have the derivative. We cannot take that as a derivative. Okay, so the interesting part is the sharp point is always appear when we have the x. So when you have a function that's having this particular pattern, x to the power of 2 over 3, this will make the sharp point. Okay, this one I just want to show you how we can get a sharp point and the vertical tangent. Okay. But let's construct in more concise way what will be the curve sketching. So it's actually 4.5. So I will go 4.5 first based on your textbook, and then going back to 4.4, the L'Hopital rule. Okay? Because I think 4.3 is about the curves, 4.5 about the curve sketching. So it's going to be connected. So I will just take that as a whole curve sketching. Okay. Now the summary for the curve sketching. Let me give you more detailed review. So curve sketching. So first of all, we start by looking at domain. So finding the of functions. And I believe you are familiar with domain. The domain means that it's set of value that is defined. Okay? It's defined on the function. And B is the intercepts. We know intercept for y-axis or x-axis, meaning is the curve going to cross y-axis or going to cross x-axis, and in which point it will cross. So you can also confirm the sketching through the intercepts also. Okay. And C is the symmetry. How the curve will look like. Is it going to have a symmetrical? If you have an even function, like the quadratic like that, of course, it's like a reflection. But if you have like an odd functions, this is probably like the cubic root, the cubic or anything that has odd function. What's the difference? Both are symmetry in their own way. This one symmetry on reflection, like a mirror. This one, we say, the symmetry if you rotate, if you can rotate, it's going to replace the other one if you rotate. So we call also this a rotational symmetry. But this is just to confirm how the curve looks like from the looks of the function, and you can know how you get the even and odd functions. You can get from here. This is even, this is odd. Okay. So the first three steps looks on the domain, check the intercepts, and think about symmetry. Okay. But actually, these three steps, maybe you want to look for the derivative first. It's okay. You can use some techniques to derive, and then later on, you can confirm and maybe review again the curve and looking at the domain, intercept, and how the symmetry is also fine. It doesn't need to be like in order. Okay. Another steps will be, is there any asymptotes? So we know that we have a horizontal asymptote, and we have also vertical asymptote. Horizontal, if you have the limit and x and maybe plus minus infinity, it depends on the condition of the curve. It's going to have some certain value. Vertical, when you have something like the previous graph, the x equals 6 is vertical, right? But this is asymptote, a little bit different. So this will be having, going to have or going to have a negative or we can approach from the left. Okay. There are one more, actually. It's called the Slant Asymptote. But let me hold this for a while. So after asymptote, now we can think on increase or decrease. So meaning we will use the first derivative to check whether the functions is increasing or decreasing and from what interval they are increasing or decreasing. And then check the max and minimum value. Or let me just write local max and min. Meaning we need to find the critical numbers. Well, both the increase, decrease, local max and min, we can take these two as one step. That's okay, because we need to find the first derivative, also critical numbers, and then we will see the interval. Also the same thing. Okay. The order is up to you. If you try from the critical number or from the increasing, decreasing, that's still okay. Still okay. So critical numbers is when the f prime c is equal to 0 or f prime c doesn't exist. Okay, that's the critical numbers. And also, aside from checking number by number, we can also check max and min through the second derivative. Or maybe it's not x, maybe c, okay, critical number. If this is positive, means that this will be local minimum. If this is negative, this will be local max. And how do we remember which one is which? We just remember that every time the second derivative is positive, it's going to have upwards. Okay? And if it is negative, it's downwards. Okay? Yeah.
In second derivative, we set it equal to 0.
Yeah. This one is the first derivative, but if you want to check the max and min, you can use the second derivative.
Yes, but do we have to set it equal to 0 or just?
If it is equal to 0, we will have the other part, the inflection point. That's the inflection point. And I think, like I told you before, I think the best way to remember how the curve will be, is it going upwards or downwards, it's like U, right? So it's like, if you take a concave upwards, so I think it's easy to remember. If you forget, like, is it going to downward or upward? Remember, it's like U, so it's upwards. And the next section is about the concavity. Concavity and inflection point. So of course, we are going to use the second derivative. Check whether it's upwards or downwards. And check the interval, right? And the concavity, when it's changing, we call it inflection point. So inflection point is where the point where concavity change. Usually, we can set the second derivative as 0, but not always. Not always. the idea is still, whenever you have a point that, when you cross a point and for example, from upward and then later change to downward, then that point is the inflection point. Usually, if there is nothing that really obstruct the graph, I mean, no asymptotes, no other things other than the ideal function that we usually have, then usually we set up the second derivative as 0, and we will get the ideal conclusion. But sometimes the graph or the functions will have some complexity, so it doesn't necessarily to be equal 0. But when you check the interval and check some numbers that's still logically accepted, then you can decide when the concavity change, then that is the point of inflection or inflection point. Okay. And of course, the last part is just sketch the curve. So from all of this, I believe it's sufficient to sketch the curve, to know whether the curve having the maximum, minimum, also having the concavity changing, or maybe knowing whether it's upward, downward. Okay, maybe we can check trying some example to see our understanding on the sketching curve. Okay? If you follow the steps, or at least you understand how you are able to compute each one or to find each one, I think you should be able to sketch the curve. Okay, to sketch the curve. The curve doesn't really need to be precise. At least all the attributes on calculus, for example, like the maximum, minimum, the critical numbers, the interval that we need to find, the upwards, downwards, as long as you mention that in the graph, and the graph is particularly similar to the descriptions, and I think that should be fine. Okay? Not necessarily to be precise, each point really proportional, not really. As long as you mention the numbers, maybe the graph sometimes having like large numbers and you need to draw really large if you make a proportions. It doesn't need to be like that. As long as it's looking correct in calculus, then it's still okay. All right. Now, let's checking this graph. Okay. Every time you have a fraction or rational functions, and every time you see the denominator having some equation like this, you should be aware that probably there will be first domain you need to check, and also the asymptote. This is the takeaway. So if we follow step by step from the previous ones, so we can write the domain. And of course, the domain is, I think, very clear that x should not be equal to plus minus 1, right? Or depends on how you are going to write this. You can also write in terms of interval if you want. Both are okay. And then the intercept, x and y intercept, right? And I believe x and y intercept, we can check when y is 0, what is x, and both are actually equivalent, right? When y is 0, x is 0, check all things here. When it's 0, it's 0, it should be 0. Okay. When the x is 0, the other part also 0. So the intercept is 0. So the only point that has intercept is at point 0. So 0 is the x intercept and y intercept. We can check also symmetry if you want. Checking f input the negative x. So we are going to have 2 and exchange all x with negative x. And we'll see that it's going to be the same as the original functions, which means this is even functions. Okay. Well, in the real case, it doesn't need to be really well structured. Well, if you do this, it's good. It's really clear. But actually, you can start with any order you want. Okay. When you see maybe you want to finish with derivatives first, maybe you can check derivatives first, and then later you can check the other points. Okay. And then we can check the asymptote. First, we check the horizontal asymptote. So we are going to limit this functions, and x is approaching either positive infinity or negative infinity. Let me write both. And then you solve this in limit, and as you can see that because it has the same variable x squared, we know that it's for sure it's going to be 2. So which means y equal to will be the horizontal asymptote. And then as mentioned in the domain, okay, as mentioned in the domain, we are going to have probably positive 1 or negative 1 as our vertical asymptote, and we can check all the possibility. So we'll have plus minus infinity for both cases. So conclusions, x equal 1 and x equal negative 1. They are the vertical asymptote. Okay, the next thing is
How do you know it's one?
it's supposed to be negative. Sorry. It's supposed to be negative and negative. This 1 and negative 1 is actually our observation on the domain. Okay, so because the domain is not defined and at the x plus minus 1, so probably this plus minus 1 will be our asymptote, and we need to check using the limit.
Why is the limit from the negative side negative?
Okay, good question. One from the right. From right here. Probably you can imagine 1.01. Check the input here. And 1.01, check here. Should be different because it's having negative. If you have from the left, maybe 0.9. 0.9, I believe, still less than 1, still be negative. Yes. Okay. Okay, just use intuition. But sometimes later, you don't really need to like confirming immediately. You can just checking, just like roughly checking. Maybe after some part on the increasing, decreasing, you can confirm, oh, there should be a asymptote here, and then you can confirm, oh, this is correct. So actually, you can analyze from every angle, and not really in well-structured order, but eventually, from all perspectives, you can confirm. Okay. So this is vertical asymptote, and then the next part is increase and decrease. This is, we can set up the first derivative. So we are going to use the quotient rule for the rational function here. So this will be 4x and x squared minus 1, and then minus 2x squared and then 2x. So will be 4x squared minus 4x minus 4x squared, and then I think it's beautifully done. We can cancel this part. Okay, hello everyone. So I think I had some error on the recording, so it stopped at this increasing, decreasing. So after we find increasing, decreasing, what we are going to do is we find the first derivative. We assume that it's going to be equally to 0 to make our critical numbers, and from this equations we are going to make our line number. Okay, and we take 0 because it's our critical numbers from here, from 4x. The most logical sense is x to be equal to 0, and for x squared minus 1 here, this will be our domain in the first derivative. So this part here will make our line number having exclude this point, -1 and 1. And then these 3 points here will be our basic observations on whether the interval will be having an increasing or decreasing. Okay, and if we find out the interval for increasing, decreasing, after we check some numbers, and then we can also check the second derivative to look on the concavity. And we take some quotient rule here, and this is the result. And now imagine this numerator will always positive, right? This is a positive function. So the only way we are going to see any change in sign is based on this denominator. So we will have positive or negative for second derivative is based on this x squared minus 1. And then we have the concavity. We know which one is concave upwards, concave downwards. And then there is no inflection point because this 1 and -1 is not in domain. We can also make this line number, of course, because we are dealing with -1 and 1, so we can actually check this. Okay. We will have a downwards here and upwards here. So this is f double prime. Okay, so don't mix up this is f prime and this is f double prime. Okay, don't mix up this concavity and the increasing, decreasing. Okay, And then next is we are going to input all the informations we have. First, we can draw the asymptotes, the vertical, horizontal, and then check the interval of increasing. This is increasing, increasing, and match with the concavity. So match with the asymptotes, match increasing, decreasing, match the concavity. It needs to be match all the essentials point in calculus. And if they are perfectly matched, then that's the curve. And the curve will be fit with the your observation and in calculus, okay? And after this part, we are actually learning something about the slant asymptote, which is asymptote that is not horizontal or vertical. And we sometimes take this as a line like this one. And the slant asymptote, as in definitions, is if we have this limit, this gap, okay, when we are approaching to infinity, the gap, okay, should be equal to 0. Then if this happens, then this line is our slant asymptote. Or to make it obvious, if you take some polynomial function and you can rewrite this, for example, this x squared plus x minus 1 over x minus 1, if you take out this x plus 2 like this one, using some polynomials method like this one, then this x plus 2 is slant asymptote. And then we are trying to deal with this x e to the x, in which this is the, if we look on the forms, this is the indeterminate forms. Okay. When we check the horizontal asymptotes, this is indeterminate forms. So we need to pause for a bit, and we are going to look on the techniques to solve this indeterminate forms. Okay. So in the early chapters, we have some techniques that we can also use. We can use the rationalizations or the factorizations. But here we are going to use the L'Hopital rule. To simply put, we are going to have the L'Hopital rule when we have 0 over 0 situation, or infinite over infinite actually. And then we can just derive the top equation, derive the bottom. Okay. How we can do that and why? This is because if we look on this fg, okay, if f at some number a is 0, okay, it's some number 0, okay, some number a is 0, and g also the same, then at this point nearby, if you look on the tangent line, if you are going to zoom the nearby point of this a, they will look the same, as we mentioned also in linear approximations, right? And then we can look on the proportions of each triangle. So imagine this is a really, really small triangle, okay? So let's zoom out the triangle like this one. Then we can have these proportions, in which this is actually our f prime and g prime, okay? Another way to look at is just take this requirements, okay? Take this all requirements, differentiable continuous for both functions. When x equal a, let's say it has to be 0, 0, g prime of a not 0. And then because this is 0, we can take this, and then multiply with this. And then we can have this limit definitions, right? This is limit definitions, and precisely this is f prime. This is f prime and g prime. So we can have this L'Hopital rule. But of course, this is not really official way to prove, okay? But it's almost official, but not really that official. It's an easy way to look at, okay? Now, if we have this kind of limit, okay, we can simply just take the L'Hopital rule, okay? And this is the basic indeterminate forms. So this is basic indeterminate forms, which has this 0 over 0 or infinity over infinity. Okay, what happens if we have this? Now this is, we call the indeterminate products, in which when we input 0, this will result in 0 and infinity. One method to solve is to make this f, and the other way is 1 over g, and make it as rational functions. So we are going to forcing this equation to be 0 over 0 or infinite over infinite. And we are going back to the original concept of L'Hopital rule, in which we can take this as ln x over 1 over x, and then because of this infinite over infinite, we take the L'Hopital rule, and we know that this is going to be 0. Okay, and your midterm will be 22 of April. Okay. Okay, I hope